start, we have been talking about products, so in particular, so just to repeat the last couple of lemmas. So it seemed that lemma, so the closed subsets of the n times the m are just the zero sets of bihomogeneous polynomials. Of sets of bihomogeneous polynomials. ING are running of bihomogeneous of sets of bihomogeneous polynomials. So why? So they are homogeneous of a certain degree in the x variable, homogeneous of a certain possibly different degree in the y variable. Okay, so now we want to use this to study these things. So the last thing we saw with this was that the diagonal, this was the lemma, the diagonal delta x, in which is just set obviously of all points p, in product x times x. So this is closed in x times x for any variety x. And as I said the last time, this is somehow what replaces for us the Hausdorff problem. So it implies that certain properties, that varieties and in particular maps between them and morphisms between them for certain aspects behave as if varieties were Hausdorff, although of course they are. And I gave the proof the other time. And so we give some corollaries which kind of confirm this viewpoint. The first statement is if I have two morphisms from the same source to the same target, then the locus where they are equal is closed in the source. So it's so let me just say it. So let phi from x to y, c from x to y morphisms. Then if I look at the map of all points p and x such that phi of p is equal to psi of p, this is closed in x. So this in particular means that if we have two morphisms which coincide on a non-empty open subset of x, then they are equal. Because we know that non-empty open subsets and varieties are dense. Okay, so that's a nice thing. Then another thing that one has often for continuous maps is that the graph of a continuous map should be closed if you have some Hausdorff space. And again, the same is also true for morphisms. So obviously, definition the graph phi from x to y dimorphism of varieties. So which means projective. Then the graph of x, the graph of phi, so gamma phi, which is just a set of all pairs of a point p, phi of p, where p is in x, is closed in x times y. So you had to, in some special case, you had seen this as an exercise, but here it's completely general. And so here we take it again as a so I had this corollary, I forgot to prove it, so let me show why the corollary is true. Let me do this first. It's so simple that I can put it here. So what is this thing? So this set is just what I claim. I can look at the diagonal in y. So diagonal of y in y times y, and this just would be, I take phi comma c. Is this the right way? With a minus 1 delta y. So this is right? So what is this? So I claim this set. So this is the set of all. This is not, I don't think this is right. So I have a map. Yeah. So I have a map. I have phi is so let me just do it a bit more slowly. This is what I want, but I claim that. So we will go to this later. So in the proof of this thing, so we look at phi comma c to the minus 1 of delta y. What is phi comma c? This was the map. You know, remember if you have a map phi here from x to y, a map c from x to y. Then this one is a map from x to the product, which just sent a point p to phi of p. So this is just a map. So phi c of the point p in x is just the pair p of p c of p. And what is the inverse image of the diagonal? The diagonal is the set of points where phi of c and phi of p are equal. So this is precisely the above set. And so it is so written here. And so it is closed because it's the inverse image of the diagonal, which is closed in x times y. Image biomorphism. Of a closed set. And we do now the same, we want to in the same way see that the graph is closed. So I say that gamma f is closed in x times y for any morphism f y. And how's that? You can again write it in the same way. So I say that gamma f, so proof gamma f is just the inverse image of f and the identity of y of the diagonal in y. Because again, this says is the set of all points in x times y, so that f of x, so all points p, q, and x times y, such that f of p is equal to q. No? That's what it means. So, and thus closed. And we can also see that the graph is indeed, so once it is a closed subset like this, we can also see that it is indeed, you can easily check it's irreducible, and in fact you can see that note, if we take the map, the first projection P1 from gamma f to x, so P comma Q to P is an isomorph. Now, if you make a graph of the maps, so it's always projection downstairs is always an isomorph, and this is obviously just you can see this because the inverse map I can just take the identity of x, comma, f. Obviously this will map precisely to a graph. So it will send a point P to P, comma, f of P. It's all very obvious. Okay, and so you can see that these two maps are inverse to each other. So this is a closed irreducible subset in x times y, which is isomorphic to x itself. Like, so to speak, in normal life outside algebraic limit. Okay, so these were some simple consequences. And now we come, let me see, yes. Now we come to the next concept, which we define using product, which is completeness. Sometimes it's also called properness, but usually properness is something about maps, not about spaces. So completeness is a property that projective varieties have, which replaces for us compactness. So it's somehow projective varieties, obviously, with the rest of the topology, will essentially never have the Hausdorff property, so it doesn't really make sense about compactness, because compactness is part of because the Hausdorff property is part of the definition of the compactness, at least if you want a useful definition. Because in the other sense, so as a matter of fact, the Zariski topology, even affine varieties will be quasi-compact, but that's of no use. So anyway, so for projective varieties, we want a property which replaces compactness, which is this completeness. And this completeness, I will in a moment say what the precise definition is, but in particular it shows, it implies that any morphism from a complete variety, so like the projective variety, to any other variety will have closed image. So this is like, if you have a continuous map from a compact topological space to a Hausdorff topological space, the image will always be closed. And so this is the analog of that. And so it's one of the reasons why one is interested in projective varieties, because they have something which, replaces for us the compactness. And in fact, it reflects the thing that if you would work over the complex numbers, and instead of k, we have the field K, we have the field C. And instead of the Zariski topology, we would use the usual analytic topology, where the open sets are just little balls. I mean, something which can, for every point as neighborhood contains the little ball. Then obviously now the varieties with this thing will be Hausdorff, and they will be compact if and only if they are complete. So projective varieties will always be compact with the standard topology. And this reflects itself in this other notion of completeness here, which we use without referring to the standard topology. So let me now define it. So I will now define the completeness, and then we will show that projective varieties are complete and draw some consequences. The bottom line will be that projective varieties are always complete, and affine varieties will essentially never be complete. So it makes for a fundamental difference between affine and projective varieties. The only varieties which, affine varieties which are complete are points. So there's completeness. So we will want to show that projective varieties are complete, and as I said, in particular, this will show that any morphism from a projective variety to any other variety will have closed image. So let me first, however, give the definition. So if I'm first in the topological setting, so a map phi from x to y between topological spaces is called closed if, well, the inverse of every, the image of every closed subset is closed. If E of Z is closed in Y for every closed subset Z in X. Okay, so this is the nice property. The map is closed if the image of every closed subset is closed. In particular, obviously the image of X itself has to be closed. Now completeness looks a bit crazy. Namely, we say a variety is called complete if if for any variety, so the variety is called X, if for any variety Y, if I take the second projection from X times Y to Y, so point PQ is mapped to Q, if this second projection is a closed map. So it means if I have a closed subset in the product, then its image is closed in Y. I mean, the projection in Y is closed. Bit. Okay, and this is supposed to be true for any variety. So, it's a property of X which has to hold, which says something about the projection to any other variety. It's kind of a priori not even clear whether such a statement can be checked in any case. At the same moment, you want to say something about, you talk about X, but you are supposed to answer a question about all varieties Y. In theory, that might even be impossible to ever check whether any variety has this property. But it's not, we will see that that's not the case. So let's look at an example of a variety which is not complete. A1 is not complete. So we can take our y also to be A1. This is just A2. And we look at the second projection of this to A1. Now we want to have to find a closed subset in A2 whose projection to A1 is not closed. And you know, you can just think of it, for instance. So we take, so this maps, if I take the zero set of x, y minus 1, so x value here, y value here, it maps it to A1 without 0, which is not closed. No, so you have this here consists of all points AB such that AB is equal to 1. So obviously you can always find for any given B, you can find an A so that this is true unless B is equal to 0. B times anything can never be 1. And so it just is this. So the picture is, if you look at it over the reals, you have here this is A2, this is A1, and this thing, the zero set of this will be some parabola like this. And if you project, you see it hits all the points except for the origin. Okay, so this is an example of a variety which is not complete. Okay, so somehow, if you could kind of think of complete, if you have this thing, somehow if you go to infinity, maybe here somehow at infinity there will be a point which hits this axis. And so in that sense it's not complete. Okay. Okay, so now the aim will be, so let me first see whether we first draw some consequences from completeness, I think. And then I will want to show that projective varieties are complete.
So if we look at the variety, which is the zero set of y minus x squared.
Yeah.
It also does not work, but in what sense is completeness?
No, I mean y minus x.
Y minus x squared.
Yeah.
So it will be projected to the positive.
Well, no, but I mean here we have an algebraically closed field, so that's not the issue. So here it looks like that because I make a real picture. But I'm always working over an algebraically closed field. So y minus x squared, that would actually, the image of that is closed.
No.
So we take the zero set of y minus x squared.
Yes.
So there is for every, so this map is actually surjective.
We're working over the complex.
Yeah, over K is always supposed to be algebraically closed. I just make my pictures of the real numbers because I cannot make four-dimensional pictures. Yeah. No, it's not a question about so otherwise the issue is more, I don't talk about what happens because the field is too small. The field is always closed. I had at the beginning of this course made this general assumption that my field is always closed.
Yeah, for some reason when we graphed the picture over R, I got confused.
Yeah, no, I was not. I just wanted to remind everybody. But yeah, so these pictures can be very extremely misleading because I always make them over R. But I don't know how would you. Well, I expect you can somehow make a picture over the complex numbers, but I can't. Okay. So now we want to show that such a thing cannot happen over the complex numbers. So you could see if you want to. So how's that? So, so we want to show that every, no, not over the complex number, that this cannot happen for projective varieties. So the theorem is every projective variety is complete. Okay, so we have to see, what that means is for every projective variety x, the second projection from x times y to y for any y is closed. So let's start with something a little bit less general. So we look at some very particular special case, namely the main step of the proof is the following, and the rest will be easy. If I take, now I write first projection instead of second projection, but you will not find that so difficult. So the first projection from Pn times Pm to Pn. So I just take product projective, so it's a special, so I don't take an arbitrary other factor, I just take another projective space, and I just do it for projective space and not for all things is closed. We will see at the end of the proof that the rest of the theorem follows quite easy from this step. This is actually kind of somewhat tricky proof. I mean, in some sense, so what we will do is we somehow do some reformulation of this using the projective Nullstellensatz, which basically restates it as something in linear algebra. And then that we solve. So let's see what we have to prove. Let x in Pn times Pm. This one. Okay. Be an algebraic set. I don't know whether I want. Okay. I think it's okay. Be a projective algebraic set. We have to show that its image. So now, so we will have to show that the image of this under the first projection is closed in Pn. Okay, let's see whether we can say something about it. So, thus x is a zero, of course, zero set. So f1 of xy, z of f1 of xy is fi of xy. So where x here stands for x0 to xn, and y stands for y0 to ym, it's just ym, it's just shorthand, which is of these polynomials which are bihomogeneous in the x and the y variables. Fi bihomogeneous. I just write in x and y. Okay. So now, to make our life a little bit easier, we want to assume, so each of these polynomials has a certain degree in the y variables. It also has a certain degree in the x variables, we don't care about that. But so we want to assume that the degree in the y variables is the same for all of them. So we can assume this is similar to something we did on Monday. All fi have the same degree. In the y variables. Why is that? Well, if some of them, one of them has the highest degree, obviously. If some of them have a smaller degree, we can multiply again by y0 to the something. We take, so write it maybe. So otherwise, if so fi has degree say d minus n in y, where d is the maximal degree occurring in the y variables, we just replace this one fi by fi multiplied by x0 to the L, comma, fi multiplied x1 to the L, and so on. Y1 to the L, and so on. So now replace fi by y0 to the L fi, y1 to the L fi, y m to the L fi, which, these things obviously have the same zero set as fi, because I've just multiplied each of them by this thing, and the common zero set of these L plus 1 polynomials y0 to the L until ym to the L is empty. So the zero set of this tuple of polynomials is the same as the zero set of fi. We used such an argument already when we proved that the zero sets of that the closed subsets of Pn times Pn are precisely the zero sets of bihomogeneous polynomials. We had a similar thing. Now, we still have to, in some sense, just find out what we try to say. We have to translate it into something we can handle. So let's go on with this. So let's say we fix a point, say P equal to, I could call it P0 to Pn in Pn. And so I write fi of p, y to mean as an abbreviation of fi of p0 to pn, so putting the coordinates of the point into it and the variables y0, yn. I just write like this as a shorthand. Then, what does it mean? So we want to find a condition for this point P to lie in the image of the second projection, of the first projection of X. So then P lies in P2 of X, if and only if, if and only if there is a point in this common zero set whose first coordinate is P. No? So this is the same as saying that if I take the zero set of f1 of p, y until n of p, y, this is not n. Because this common zero set is precisely the points in Pn times Pm whose first coordinate is p, the one in Pn is p, and which lie in the zero set of these polynomials, so which lie in X. No? So this thing is the set of all PQ. So all whatever. This, if you want, this is X intersected with P2 to the minus 1 of P. Okay, so now, and you know, obviously if this set is not empty, then it lies in the image. So now we want to see that somehow this gives us, what we want to know is that whether we can, the fact that this thing, that this is non-empty, gives us a closed condition on P in X. So how could this be? So now we apply the projective Nullstellensatz. What does the projective Nullstellensatz say? So we get that the zero set of some homogeneous, so these are homogeneous polynomials in Y. No? So the zero set of homogeneous of a set of homogeneous polynomials is empty if and only if the ideal generated by them contains all homogeneous polynomials of a certain of degree d for some d. So if I make the contraposition, then this means this is equivalent. So this statement here, P in P2 of X, is equivalent to, if I take the ideal generated by F1 of P y until Fr of Py, does not contain, so I mean, all monomials of degree S for all x bigger than 0. So for all s bigger than 0, this does not contain all polynomials of degree s. So maybe I call star s the thing for one fixed s. So this is star s is the condition that this idea does not contain all polynomials of degree s. So of degree s in the y bracket, in the yi of degree s. And so we have, so we want to show that, so that means now, thus, we find this implies, if I take the second projection of x, this will be the set of all points P in Pn such that P does not fulfill the condition star s for all s bigger than 0. Okay, which is the same as saying is the intersection over all s bigger than 0 of the set of all points p in Pn such that p. No, the condition is does not contain, so it fulfills. No, sorry, I wanted the opposite. The condition was that it does not contain all monomials, but that's the positive condition. So P fulfills. Starts. Okay. So this P2 of X is the intersection of these subsets. So therefore, it is enough that each of these sets is closed, because then it is the intersection of closed subsets. So I maybe can first say, so this the condition star S so here we have assumed that the Fi have all the same degree, and this degree I want to call D, as I also used here. Okay, so this D is the degree in Y that all these polynomials have. So star S is trivial for S smaller than D, because obviously if all these polynomials have degree bigger than S, then this ideal generated by them will not contain a single monomial of degree S. And so certainly for every point in Pn this condition will be true. So we only have to check this for S bigger or equal to D. So now let S bigger or equal to D. So we fix. And now we have to show that this set is closed. Set of all P in N, P fulfills. Is closed in P2, in Pn. So we have, for now, it seems we have a relatively simple question whether P is in the image of the second projection, and we have now managed to write it down in a much less attractive form. It looks somehow much uglier and more difficult to understand, but anyway, it's easier to check. So we have to check, we only have to show this. For any fixed S which is bigger equal to D, we have to show that this is closed. And now we reformulate this as linear algebra. So remember that the second factor was Pn, no? So we were in Pn times Pn. So this Y stands for the variables Y0 to Ym. So first denote it happens to be M plus S choose M monomials in the Yi of the PS in some order by Ni of Y for I goes from 1 to M plus S choose M. So choose all the monomials of degree S. And we have to see that about the condition that not all of them are continued. So these are one thing we want to look at. So what are the elements of degree S in this idea that we are talking about here? The elements of degree S in Y, in this idea, in the idea generated by F1 of Py until Fr of Py. Well, these are all the these are all the elements which we can write as linear combination, which we can write by multiplying an element here by a monomial. No, they are a basis of this are given by multiplying one of these by one of the monomials of the corresponding lower degree. So the linear span of the set of all there's a misprint here. No, so I made a misprint here. So this thing was supposed to be called MI. I want this to call this MI, not NI. And I went ahead of myself because I first wanted to write something else. I also want to keep track of the monomials of degree S minus D. So denote Ni of Y for I from 1 to M plus S minus D choose M, the monomials of degree S minus D. In the Y bracket. Okay, and now I come to what I wanted to say. What are the elements of degree S in this ideal generated by this Fi of Py? Well, how do we get them? We just have to take their span by taking any of the generators and multiplying by a monomial of the complementary degree S minus D. So this is just the linear span of all the Ni of Y times Fj of Py. No, I is from 1 to, what was it? And what was it? M plus S minus D, and J is from 1 to R. So just the linear span of these. These are all the elements of degree S in this state. I mean, they could be different, but anyway, the linear span of this. And so now instead I consider, instead of putting here the variable P, we just consider also the corresponding polynomials. We put back the variable X. So I denote the product, so Ni fy times fj of xy, so now it's polynomials, by, so all of them by, I call it gk of xy, and now we know there are quite a few of them, namely k goes from 1, I just write t, but t is equal to m plus s minus d, is s minus d. Or I could write s minus d, it's the same as putting m, but before I put m, times r. Okay, so we have all these many polynomials, all the possible products, and now we can in these terms say what this idiotic condition means. We will not wipe out the condition if I can. So in these terms, the condition star s is equivalent to, well, the condition is that this linear span is not the whole of this. No? Because it says this does not contain all the monomials. So in other words, equivalent to saying if I take gk of, again, I'll put back p, x is set from k equal 1 to t, and does not generate the vector space of all homogeneous polynomials in the y variables of degree s. And you know, so this means, so this condition here is that if I just take the collection of these things, the vector space generated by them has dimension smaller. In other words, or equivalently, its dimension, the dimension of this vector space of the span of the gk of the x y is smaller than m plus s gz, no? The space of all polynomials of this degree. Okay. So we still, our aim is to show that this set is closed. And now we can use linear algebra to show that it's closed. So I write this polynomial gk of xy for any k. This is a polynomial in the x variables and the y variables. So I can write it as a, as a linear combination of the monomials in y, where the coefficients are polynomials in x. So I can write this equal to sum I equals 1 to m, so m plus s choose m, so as many monomials. We have some polynomial a I k of x, where this is a homogeneous polynomial in x, and x homogeneous polynomial in the x variables, times the corresponding monomial, which we had called mi. So we can write it in this form. So what is now the dimension of this linear span of this. So the dimension of the linear span of the GKEY is what? So is the rank of the matrix of this matrix. If I put P in the variable, A, I, K of P, so the x variables are replaced by x, where I goes from 1 to m plus s choose m, and k goes from 1 to this t. So you have this huge, enormous matrix, and if I put P into the matrix, then the dimension of the linear span is equal to the rank of the matrix. So therefore, if I look, so therefore the condition star s, which means that the dimension, that this linear span is not equal to the whole thing, or in other words, that the dimension of the linear span is smaller than this, is precisely saying, is conditioned to the, is equivalent to the condition that the rank of this matrix is smaller than the maximal possible rank, which is m plus s choose m. Is equivalent to the rank of A, I, K of P, again of I and J, so the matrix is smaller than m plus s choose m. So that means the set of all points P which fulfill the condition 1s, star s, are precisely the points for which the rank of the matrix is smaller than this. But this is the zero set of a set of polynomials, namely of the minus of this matrix. So thus, the set of all P and Pn such that star s holds for P is the zero set of, so the common zero set of all m plus s choose m times m plus s choose m minus of this matrix, of the matrix A, I, K, where now I don't put P, but I just put the variable x, Ij, so I goes from 1 to m plus s choose s, choose m, or s, whatever you want, and j, k goes from 1 to t. So this is just the, and so each of these minors, so you have this big matrix, you take, so the minor is the determinant of this corresponding submatrix, so this is a homogeneous polynomial of some degree. So it's a common zero set of some homogeneous polynomials of degree d. So these are homogeneous polynomials. In the x variables, thus this set is closed in Pn. imagine that star S holds hockey is closed in here. And we had seen, so this is not closed in here. And we had seen from that that, as it is just an intersection of such as the second projection of X is just the intersection of all these sets, it is also closed in Pn. So this shows that, so we find that if I take the map P2 from Pn times, so it actually took P1 from Pn times Pm to Pn is indeed closed. So this was quite a lot of work, and I mean, so mostly we kind of made this translation into linear algebra, and then in some sense, it's not particularly deep, but it's just a little bit much. But anyway, now we have done it, and so the main tool that we used was the projective Nullstellensatz, and otherwise we had to we used that to translate it into this linear algebra, so that in the end our thing is a zero set of the minus of some matrix, and so therefore closed. Okay, now we come to the rest of the proof. We want to show that indeed every projective variety is complete, which is a bit more than just the second projection from Pn, or the first projection, whatever. Obviously that makes no difference, being a closed map. So now we first want to show that Pn is complete. So let Y be a variety. So Y could be a subvariety of a fine space, or it could be a subvariety of projective space. But if it's a subvariety of a fine space, I can embed it into projective space, because a fine space lies into projective space. We can assume that Y is a subvariety of projective space. So we can assume Y contained in some projective space, say Pm. It doesn't have to be closed in Pm, because if it was closed, Y would be projective, but it can be locally closed. So an intersection of open and closed. So it requires projective variety. So now we have to show that the projection from Pn times Y to Y is closed. So let Z be a subset of Pn times Y be closed. So note that this lies in Pn times Pm. So we can take the closure of Z in Pn times Pm. Nobody can hinder us from that. And then obviously it follows by what we already have. We take the second projection of this C bar, this will be closed in Pm, because that's what we showed. So how is this related to our original problem? So if we take the second projection of Z, want to relate it to this, well, this is the same as taking the second projection of this Z bar and intersecting it with Pn times Y. No, because a closed subset of Y is the intersection of it with its closure in the ambient space. So that's how it has characteristic topology after all. But what does that mean? So this just means that this is the same. If I do like this obviously is just the second projection of C bar intersected with Y. And so this is an intersection of a closed subset in Pm with Y. So it's closed in Y. Okay, and so this shows that Pn is complete. So here was no actual argument, just some kind of simple tricks. No, there's no. Now that even simpler tricks show that every projective gravity is complete. So finally, let X, say Pn, be a projective gravity. So again, let Z in X times Y be closed, where Y is any gravity. Now we can take the closure of Z in Pn times Y. No, we certainly can do. No. No, I don't know why I said that. I kind of skipped it. So we have this. So note that X is a projective variety, so it's a closed subset of Pn. So X times Y is closed in Pn times Y, and Z is closed in that. So thus, then Z is closed in Pn times Y. And so therefore, by part 2, the second projection of Z is closed in Y. So this is even kind of trivial. No? So we just have Z is closed in this, and this is closed in Pn times Y, and so therefore we just apply the previous thing and it gives it without any effort. Okay, and so this proves the statement. So now we want to draw a few consequences of this. So one of the consequences of completeness is that the image of a morphism starting from a projective variety is closed. And this should be clear to you. Why? Because the graph of a morphism is a closed subset. And the image of the map is a second projection of the graph. So let me do it. So corollary. Let, say, f from x to y be morphism of varieties with x projective. Then f of x is closed in y. And as I said, it is clear that the image of X is just the second projection of the graph of F. No? It's just, the image, this is just a set of all P F of P. The P is in X, and obviously if you project it, you just get the image. And this graph, by what we have seen of any morphism, is closed. So it follows by complete. Okay. And now we want to, as I kind of announced, we want to deduce from that projective varieties are somehow very different from affine varieties, and that basically there is no intersection between affine and projective varieties. So, what I want to say is, obviously by definition, a projective variety is something, and a affine variety is something else. But one is always interested in things up to isomorphism. So a projective variety can never be isomorphic to an affine variety, unless they are both points. No, any two points are isomorphic. But except for such a trivial thing, it can never happen. So they're really of a different kind. So the first thing is also something which I said corollary. Well, I don't know why I can't write English anymore, but anyway, corollary. So first, every say regular function on a projective variety is constant. So if you have a function, so a regular function, as you know, is just an element, a rational function, so a quotient of two elements in Sx, which are homogeneous of the same degree, but so that the denominator doesn't vanish, so that the denominator doesn't vanish anywhere. I mean, that you can choose representatives so that the denominator doesn't, for any point you can find a representative that the denominator doesn't vanish there. And then, amazingly, such a thing has to be constant. So regular functions don't really, regular functions which are regular on the whole of a projective variety don't really exist. They are just the stupid ones. So somehow O. So regular function means it's regular on the whole of it. No? So O of X is equal to K for projective variety. Okay. And we would be what? Huh?
Sorry, what was this?
What was what? So,
oh, yeah.
So if X is a variety, X projective, so it's just a reformulation of the same, and it follows that OX is equal to K, the constant function.
Is this somehow related to the Well theorem?
Well, yeah. So you, if you work over the complex numbers, you can, if you have a projective, so there's some kind of, if you have a complex submanifold of projectives, well, it is somehow related. So it's somehow, if you look at it over the complex numbers, so such a function would be essentially a bounded holomorphic function on this thing, only that it's in several variables, but still a bounded holomorphic function. And so by Liouville theorem, such a function has to be constant. And so it is somehow very similar to the Liouville theorem. It's over the, if you, instead of doing it in the algebraic setting over algebraically closed field, you do it over the complex numbers, it is a manifestation of the Liouville theorem, or maybe if you want a generalization of that.
So, if we express it like somehow establish a connection, this would be a holomorphic function for this thing. But do all regular functions like map surjectively to all holomorphic functions? Or?
No. So there are more the thing is, the claim is that the global regular functions, so which are regular on the whole thing of projective variety, are just the constants. And so obviously that are the same as the holomorphic functions. But if you take an open subset of a, say, complex manifold of just P1 or whatever, then the regular functions on that are much fewer than the holomorphic functions. You know, something like the exponential function is not a regular function. You cannot write it as a quotient of polynomials. No? And so there are many more, but somehow there is some kind of theorem, which I cannot precisely explain how it works, that for many, which is sometimes called Gaga theorem, which says, which was also some kind of joke because it's by some French guy, and Gaga in French also means crazy, and which says that for many means and purposes you could pretend that the holomorphic functions are the same as the regular functions. So if you pretend this in several places at the same time, everything becomes correct again. Obviously, so this thing itself is not true, but if you do, the results which you deduce from that, if you do certain things, will always be correct. There's a theorem which states that, but obviously, the actual statement is in terms of coherent sheaves, so I cannot really explain what that would be. But there is some statement which makes some kind of sense of what you said, but I cannot explain it possibly because it's not. Okay. Where was I? So let's see, and then as a consequence of that, actually, we see that there's somehow no morphism from a projective variety to a defined variety. So that means, second, every morphism Cp from x to y from a projective variety to a defined variety is constant. That means it maps x to one point. So there's no non-trivial map from projective variety to a defined variety. If you have a morphism from projective variety to a defined variety, it has to map everything to a point. Obviously, the map which maps everything to a point from any variety to anything else will always be a morphism. But that's kind of stupid, no? But if you want anything non-trivial, it doesn't exist. And so, in particular, if x is projective and isomorphic to a defined variety, then x is a point. Okay, so there are no intersections between projective varieties and varieties isomorphic to affine varieties, and even kind of the thing, there's even no way to go from one to the other via morphisms. Okay, I mean it's a big state, so it's surprisingly easy to prove. There's not really much there. So let's take a Reber function. So we have x is a projective right here, we call it x. We know that a regular function is just a morphism to A1. So now we have a morphism from x to A1, so it's a closed map, so the image of f must be closed. But we know precisely what the closed subsets are. I mean, it also has to be reducible. So it either would be a point. So the image of a morphism is always irreducible. So it must be either a point or the whole of A1. So we have to exclude that it can be the whole of A1. But note that we have a A1 can be viewed as a subset of P1. So we can view A1 as a subset of P1, thus F is also a map from X to P1, which just happens to map into A1. And also, as a map from X to P1, the image must be closed. So thus, also, f of x in P1 is closed. But obviously, A1 is not closed at P1, so the image cannot be A1, and so it has to be a point. Okay, so every regular function is constant for this with this argument. And now the second statement is even easier because we know that morphisms to affine space are given by an n-tuple of regular functions. Each of them is constant, so the map is constant. So we can assume that y is contained in A and say, thus we also have a morphism phi from x to an, by just the morphism to y, we have morphism to an. So then we know that our phi can be written as f1 to fn, where the fi are regular functions on the whole of x. So each of them is constant, so the map is constant. Okay. Yeah, so yeah, now I mean it's a bit less time, but I think maybe I will stop now earlier, and the next time I